Then, hello everyone. It's my great pleasure to welcome all of you to the very first international online seminar on interval methods in the new calendar year. And today's speaker will be Goran Frehse, who is professor at ENSTA, the École nationale supérieure de technique avancée, Institut Polytechnique de Paris. And he is not only professor, but also director of the Computer Science and Systems Engineering Department at ENSTA. And he's especially interested in approaches for formal methods in verification, especially with applications to cyber-physical systems. And yeah, we're looking now forward to your presentation in robust deterministic abstractions of discrete-time continuous state systems through linear state feedback. Goran, the floor is yours.
Okay, thank you very much, Andreas, for the introduction. So, Happy New Year to everybody. We're in 2025, and this is the first time since the new year that I'm speaking. I just realized that I have to adjust all the titles because ENSTA Paris has joined ENSTA Paris, ENSTA Bretagne, to form a single establishment, which is now ENSTA. So I have to update the bio information. So thanks for coming to my talk. I want to share with you some thoughts, some work about discrete abstractions. A little bit maybe on my background. I've been working on reachability for quite a while and always in continuous spaces. And my main reason why I was not so tempted by discrete abstractions is the state explosion program. And so what I'm showing now is sort of my late entry into this discrete abstraction field, where I want to show a heuristic that helps avoid the state explosion problem a little bit. And why am I mentioning this is mainly because I know that there has been many decades of research in this direction, and I fully recognize that other people have tried to do similar things. So if it seems like I'm reinventing the wheel, then it's because it's probably true, right? But I still, at the end, I think the result that we present at the end has so far not been shown. So bear with me through the introduction. So we've come from this to this topic from online verification. So our classic way to verify systems was to model the system with some automaton formalism, some kind of formalism that captures all the behaviors of the system, and then do offline verification, meaning that before even running the real thing, we analyze this model and say, okay, it will never ever do something dangerous or unsafe. And that turns out to be a hard problem. And so a few years back, we got interested in online verification, where you can use the information, what the current state is of the system. And typically, you just look ahead for some finite horizon into the future to say, okay, it's going to be safe over this finite horizon. And basically, so the information of where you're currently at and how far you look into the future helps cut down on the complexity of the thing. So this is the online aspect. And then we thought, so if you want to build a universal monitor, something that says, okay, let the controller do what it wants to do. Usually this is for optimizing performance. Yeah, there is some nominal controller that optimizes of performance. And what we want to do is just monitor and intervene only if this would lead to dangerous behavior. Okay, and after much thinking, this monitoring has some you run into problems if you keep in the continuous state space. We ended up going back to discrete abstractions, basically to have guaranteed results in a finite number of steps. So now here I am with discrete abstractions, and as I said, I've been trying to avoid this for decades. So my main point was, okay, how can we avoid and error accumulation and wrapping effect and those kind of things. Okay, so basically we want to have something that's as coarse as possible in terms of an abstraction, so that it's a small model, but at the same time we need to be precise enough to capture things like safety and the things that we want to do. Okay, so this has been a long preamble. Now let me define the objectives. We want to make an abstraction, okay, and now it should be robust, so that it should be able to account for measurement errors and all model uncertainties and all kinds of other things. But it should be deterministic. Why deterministic? Because we want to be able to enforce behavior on the system. So if the system is on its way to a dangerous region in the state space, we want to be able to guarantee that we can get it back or can keep it in the safe region, and that's easiest if you have a deterministic abstraction. I'll get back to this later. Okay, and then the question is, of course, how do you get this abstraction? And here I take my standard tools that I've been using for years, which is piecewise linear over approximations. And the other thing will be feedback controller. I will get back to why this came in. Okay, so basically we want to build these abstractions, and the perspective of using them is as supervisors. Okay, to supervise the system to make sure that it stays safe. But not only safety, but also other properties. So let me set the formal stage for this. It's relatively standard. So we have the state space is just Rn. We'll be working with sets of states and sets of inputs. And the dynamic of the system here, F, is a mapping from a set of states and a set of inputs to a new set of states, so the successor states. And this model is complete in the sense that there's always a successor state. There's no blocking. You know? If you're in a state X and we apply one of the inputs U, then you always end up somewhere, and you don't ever end up in an empty set. So with this operator, we can define trajectories. And so we have these inputs that we get to choose. So any kind of controller can be written as a policy. So the policy maps the states to new inputs. So if we know that right now we're in a state X, the policy tells us what inputs can be applied. And if you want to use this for supervision, then the policy gives us a set of inputs. Okay, and so if the nominal controller proposes an input that's inside the sets of available inputs, then that's what gets applied to the system. And if not, then the supervisor chooses one of the available inputs that are safe. Let me jump right into an illustration of what this would look like in practice. This is just an illustrative example for inverted pendulum that's controlled by a PID controller. And so in an unconstrained system model, let's assume we linearize this around the equilibrium point. Then this the PID controller can stabilize the system. So in an unconstrained system, this is a very easy problem. But now, if you say, okay, my inputs are actually constrained in the physical system, there's only so much energy that you can put into the system, then the picture changes. Okay, so here in the illustration, can you all see my mouse, just to be sure?
Yes.
Yes,
Yeah.
that's working.
So the equilibrium would be here in the center, and you see some random trajectories from states that are randomly sampled. So if the system would be here, then this PID controller would bring the system back to the equilibrium. And now, because of the input constraints, the stable zone is actually constrained. So there's these black lines that indicate outside of the black lines, because of the physical constraints, there's no way that you can get back to the stable to the origin. Okay, so outside of these black lines, these red regions, there's nothing we can do. Nobody can save our pendulum. Okay, but there's an interesting zone that's illustrated here in yellow, and that's the zone that if I just apply the PID controller input as if there was no constraints, it takes me outside to this red region and the system is lost forever. Okay. Whilst if I have a supervisor that intervenes, so basically it's on this border here, on these border states. So the supervisor intervenes, and instead of the nominal input, he replaces it with an input whose job it is to just keep in this safe region. Then the system is safe. Okay. So again, the PID controller applied to a system with constraints is unsafe in the yellow region, but if you pair it with a supervisor, okay, a very simple supervisor that just substitutes the actions that are unsafe, then it's safe inside the black lines. Okay, and this is basically what we want to do. So designing these supervisors is a hard problem if you want to actually prove that they work, that they do their job. Essentially, you need to synthesize a controller. In the literature, and I try to simplify a little bit, but basically in the literature, there's mostly a three-step approach. The first being that you create a discrete abstraction of the continuous system. Then you solve the synthesis problem on the abstraction, basically you on a discrete system. And for the sizes that we look at, this is a relatively easy part. And then the third step would be to apply the solution, meaning the policy, back on the continuous system. Okay, so you pass from continuous system to discrete system. Okay. And now the question is, if you want to be formally rigorous about this, how do you relate the continuous system to this discrete abstraction? And the classical tool to do this would be to have a bisimulation relation, meaning anything that can happen in the continuous system can also be reflected in the discrete and vice versa, okay, in both directions. Now, this is really tricky. There's been a lot of research about which types of continuous system, for which types you can even do this. Okay, so it's generally may not be possible. So instead of really asking for bisimulation, there's been some relaxations that have been proposed. Okay, and one of the notions that has gained a lot of attention is alternating simulation. So alternating simulation means that if you choose a an action in the abstraction, you can actually realize this in the continuous system. So actions are enforceable. Let me just give a quick characterization of these notions. So you have a simulation relation. Basically, we look at labeled transition systems, so just graphs with labels on the edges. Okay, and so we have the continuous system is an infinite state labeled transition systems. The discretized system is a smaller labeled transition systems. If you're in a bounded domain, we can even make it finite state. Okay, and so what would be the relationship that we want is that if I look at condition 2 here, anytime there is an action from state 1 to state S1 prime with some action label U1, so this would be the input, then there should be also in the abstraction a transition in the abstract system with possibly another input. They don't have to be the same, such that the successes again are in the relation. Okay, and if this condition holds in both directions, so basically if R is symmetric, then we have bisimulation. There's one more thing here, and this is the output function. So if we talk about like what is observable and how can we gain access to the state of the system, we can talk about this output function. So the concrete system has an output function and the abstract system has an output function. And in our formalism, we say that any output in the abstract system has also to be an output in the concrete system. Yeah? This is about this enforceability. We want to say, okay, if we say we can generate this label in our abstraction, then we can also generate this output in the concrete system. Now, the simulation in the way that I showed is in the sense that anything that's possible in the concrete thing should also be show up as behavior in the abstraction. This is very essentially important for safety. So if there's some unsafe thing that's possible in the concrete system, then you should be able to see it in the abstraction so that you can avoid it. No? Now, alternating simulation goes in the other way. Alternating simulations is about saying, okay, if you can do something in one system, you should be able to do something equivalent in the other system. Okay, so and here typically the roles are inversed. Okay, so an alternating simulation over two systems, so L1, L2, it guarantees that any action in L1 can be enforced in L2. And so in the story that I just told, L1 would now be the abstraction. We want our abstract controller, abstract system model. If there's a path back to some say the initial states, and we want to enforce this path, then we have to be able to find a sequence of action that also realizes this in the concrete system. And this is what alternating simulation does. Okay. Now, this definition would actually be easy if it were not for non-determinism. You can see here that now in the conditions there's these quantifiers. Okay. So if you apply, if we say that there is an action in our concrete system, then applying that action should always, in the presence of non-determinism, also lead to states that are in our simulation. And this is where it gets a little tricky. Now, this is all well said and defined on these infinite state labeled precision systems, but we want to compute with a finitely many operations. So we don't want to enumerate these things. Instead, we want to compute with sets. And as I've defined the system in the beginning, if you have a successor operator f that maps sets to sets, then this can be done, yeah, using set calculations. And so here in our abstraction, basically we now say, okay, so if we have sets of states, what should be true, mapping these sets. And this leads us to the concept of reset abstraction, which is basically saying, okay, we follow the reachable set of states. The reachable set of states is that for any set that we capture any possible successors in this, applying this set map F. Let me illustrate this state explosion problem with a simple graph. Traditionally, a lot of this discrete abstraction work has worked with partitions of the state space. Here, I've chosen just a rectangular grid, but it doesn't have to be rectangular. And but the problem is the following: say we start from some initial state here shown in blue, okay, and now our operator f maps this to a new set. Here, this set, okay, and now we map this back. We map this to a discretization. Say the discretization is the cells of this grid. Then we started out with a single cell, okay, and because the image of the cell overlaps with more than one other cell, here in the image, for example, we overlap with 4 cells. Now we have 4 successor cells, and the image of each one of those 4 will probably also have 4 successors, and so we get a sort of an explosion in the number of successors on the order of 4 to the k, where k is the number of iterations that we take. Okay, and this is what we want to avoid. Now, what would be the case where we don't have this? Okay, again, here in the top of the picture, we have this this case where we have a single cell, which we can describe as a ball around the center state. Okay, and this gets mapped by our operator f to some shape. Here it's a diamond, but it could be some other shape, and this diamond overlaps with more than one cells. Okay, and in our abstraction, because we said we need to be able to see all the possible successors, but this means that we need to have 2 abstract successor states, since we overlap with 2 cells. Okay, this would be the classical, easy, in quotes, way to define this. Now, if we say, let's try to not have any explosion in the number of sets here, the only way we can avoid this is to say, if we have a single cell, it needs to be mapped to 1 single abstract state, so not many. So this is what we call a deterministic abstraction. So f maps to exactly 1 new cell, and so we don't have any explosion in the number. So this is what we want. Now, the way I'll get to the conditions in a second, but basically the way we go about this is that we don't partition the state. What we do is that we have overlapping abstractions. Okay, so the red would be a partition. Okay, the red grid, and what we have is the blue grid. Now it's not easily because of all the overlaps. It's not so visually easy to visualize. So I just drew 2 abstract states. You see that they overlap and they're larger than the partition cells. Okay, and simply being larger means that our target set f, it can now lie within within the blue set, and the blue set is bigger, so we can ensure by making it big enough that it actually fits in a single successor cell and not many cells. I need a little bit of notation for the sequel, so we will describe for convenience these cells as balls. So we have some set and then enlarge the set with a ball of size alpha. Alpha here would be the spacing in between the grid points. The set of grid points is x hat here. Okay, so we have the centers of these balls, and they're with spacing alpha, and then the size of the blue cell would be epsilon. Okay, so we have alpha is the spacing, epsilon is the actual size of the abstract sets. And of course, if you want to cover the whole continuous state space, then we always have that epsilon is larger than alpha. Okay. So we now have a space discretization with basically the centers of the abstract states and the balls around them. Okay. And similarly, we discretize the set of input. So we have discrete points, and then with the balls around them, they cover the set of inputs. I'll jump right into the results. So if we take these conditions for abstract simulation, you remember there was this successor operator f in there. If we break this down to the condition that we always want f to be contained in one of these abstract cells, okay, basically we need this, and to quantify how much f can enlarge the set, we assume that it's Lipschitz, so we have constants kx and ku that say how much larger it can possibly get depending on the diameter epsilon of our cells, and this is better would be diameter of the input region that we take into account. And so what comes out of this is that if kx is smaller than 1, basically meaning that f, the operator, is contractive in the states, then we can always achieve this deterministic abstraction by selecting an epsilon that is large enough. Okay. So it has to be large enough to do what? Well, it has to be large enough to compensate for the enlargement due to the inputs. We consider a set of inputs, so it has to cover all possible inputs. It has to be large enough to cover W. W is the non-determinism. Okay, the non-determinism would be the non-controllable. So the increase in the size f that's not due to the inputs, and alpha is the spacing of the grid. Okay. So for any contractive system, okay, you choose your spacing of the grid alpha, and this formula gives you the epsilon, the smallest epsilon where you can say, okay, here you're guaranteed that you always have just one successor set, okay, instead of many. Okay, fine. Now, what is interesting about this is that this contractiveness condition is actually pretty much the same as what other abstraction approaches have proposed. So we try to impose this determinism and say, okay, let's force the system, this abstraction, to be deterministic. What are the conditions under which we can do this? And more or less, we get the same conditions under which all the other approaches also work, which did not require determinism. Okay, so we have not so far done anything particularly powerful, except that we get this determinism for free, in a sense. Okay. So here's another illustration to just show this condition. Say we have this abstract cell in blue, and F maps this to this black diamond. Okay, then the conditions ensure that taking into account all the non-determinism and everything, you lie in some other new blue cell, okay, which is bigger than the grid size. Okay, so we have the result that this works if the system is contractive, and okay, fine. But of course, in generally, the systems, they are not always nice and contractive, at least not globally. So the question is there something that we can do about it? Okay, so now let's say our system is not everywhere contractive. So now the idea that we follow for non-contractive system is to use state feedback. Okay, let's add a feedback controller that makes the system not necessarily contractive everywhere, but tries to make it more contractive than it is. Okay, I'll go back to the conditions later. And to formalize this, we introduced the notion of a policy abstraction. Basically, what we say is, instead of having these, this is the same definition as alternating simulation, which is used standard in the literature. But now what we have here is not the actual inputs that are applied to the system, but the policy. Okay. So here, if there is a policy in the abstraction, then there should be a policy that works in the concrete system. And this just allows us to work efficiently with policies on the labels of our transition system, rather than individual actions which should be predicated on the state. So in other words, here the S here is an abstract state, but pi is a mapping from concrete state and not a mapping from an abstract state. Okay, so it simplifies the notation a huge. Okay, so now we want to do feedback. Okay, fine. What would be the simplest way to do this? Well, would be constant state feedbacks. And we, in the end, okay, spoiler, we want to get to linear conditions about when this works. So let's consider a linear approximation of F. Now, this does not have to be a linearization at all. Okay, we simply need 3 elements. Okay, so one is a state matrix. So this could be a linearization, but it doesn't have to be. Linear matrix B characterizing the dependency on the inputs. And then this big thing here is where all the rest comes in. So if A and B come from a linearization, then all the linearization error could be in here. You can also simply say A is 0, B is 0, and put everything in here. Okay, so what's in here? It's a constant term. Okay, so if the first term is 0, then we just say, okay, F is inside a ball of radius omega. That would be one way to have it. Yeah. But you can, another way would be, okay, F is inside a ball of, and now the radius depends on the radius of the set that you're passing to F, and the set, so the difference to the normal X and the difference to the normal U. So basically we have a way to add linear dependencies, and then here a constant non-determinism plus a linear non-determinism. And how you get this is for the remainder of the approach. It doesn't matter. You can get this from linearization or from other things. Okay. So we said we need these linear bounds basically on what F does, so that we can later have a nice system of equations that we can solve. What do we do with the policy? We said we linear state feedback. So the policy X for concrete state X, it gives a set of inputs, or actually just one input, and the input is the nominal one minus, and here's the state feedback matrix. So it's basically feeding back the state deviation from the nominal state to the concrete state. And now there's a little trick in here. This is divided, the difference between the nominal state and the actual state is divided by the diameter. And this is a trick because later in the conditions I will show this will multiply out and make it so that the conditions are linear, right? So you can, if you want, you can ignore this for now. This is just a little math trick. Okay. So we have a feedback policy. Okay, and so now the question becomes how can we choose this feedback matrix K? Okay. Again, we turn to our definition of what the alternating simulation should achieve. Okay, recall that all the successors should be in the following state, etc., etc. Then we have a saturation constraint because our feedback matrix should not lead to inputs that are physically not realizable. Okay, so there's constraints on the inputs. This is this part here. Okay. We want to be complete. So when we choose a size of these cells, so epsilon was the size of the blue cells, it has to be greater than alpha so that we cover all the state space without holes. And there's an artificial constraint epsilon max in there simply because this helps us with the boundedness of the problem. Yeah. So epsilon has to be bigger than alpha. That's the central thing. Okay, and then basically we say, okay, if we apply F to a state and with this policy, this feedback policy, then there should be some nominal state X hat prime. So one of these blue cells, the center of one of these blue cells, such that the distance between them is smaller than epsilon. So this guarantees that there's always a blue cell that contains the image of our states. Yeah. And if we now substitute all the previous definitions into this condition, we get this big thing. There's a lot of norms in there. And now we've used the infinity norm, which basically means that this entire thing is just a conjunction of linear constraints. Okay, if you, with some tricks, you can all these conditions, you can write them as a linear constraint system. Okay, and so what this gives us is for all the variables. So the variables would be typically the feedback matrix that we want to do. Then we said we need to know how big do we need to make the blue cells. Clearly, we want to make them as small as possible. We want to be precise. So we need to find the feedback matrix. We want to know how big we need to make the blue cells. Well, all of that comes out of this constraint. Okay. Now, there's actually two ways to go about this. One would be to say, okay, let's just do a feedback controller since we want small sets. Let's just do a feedback controller that produces the smallest set possible. Okay, and this is certainly we could solve this problem, and we have. But it turns out that having the smallest set does not always lead to a solution in this case. So what happens is that if you contract as much as possible by choosing a K that's very contractive, okay, then you're using all the inputs to achieve this contractiveness. Okay, and you don't have any degree of freedom to visit different states. You just contract, but if you use you have this limit on the set of inputs. So there is no more freedom on applying other inputs. Whilst if you make this feedback matrix smaller, okay, this gives you some margin. So there's some input left in quotes, so that you try to visit a different state rather than the one that the contractive input gives you. Okay, and so visiting different states is certainly a goal. I will show this in examples in just a moment, but I wanted to drive home the point that just trying for contractiveness without looking at the rest doesn't work at all. Okay, we tried this. So it's really key here to say, okay, let's write the most general conditions that we can get and choose the feedback according to the general conditions. Okay, so what are the general conditions? So we basically say, what are the transitions that we would like? Okay, so this is a transition would be from an abstract state x hat to another state abstract state x hat prime, given some nominal input u hat. Okay. Does this condition hold? So is there a feedback matrix that realizes that the image of our operator f is fully inside the target state? Okay. So this is for each transition. So for each possible transition, we need to satisfy these conditions. And this is the previous one plus the constraint on the inputs and plus this completeness thing that we want to cover our states. Okay, and so we get a huge conjunction of linear constraints. And if they're satisfiable, then we have a realizable abstraction, okay, that it takes care of all the possible successor states under non-determinism. Okay, and the feedback matrices that we need to realize this, they come out of the solution as a side product. Now there's one more thing you can actually, if you look at it, this is also linear in u hat. Okay, so we can leave u hat, so the nominal input here, as a variable, meaning that we can just choose pairs of states. Okay, and we can try different pairs of states and say, does this have a solution for this pairs of states? And if yes, then we include this transition into our abstraction. Okay. Now, if I've convinced you that this big set of linear constraints is enough to guarantee that my abstraction actually is sound and it works, okay, the question still remains, okay, so which would be the set of transitions for which this holds? And this is not a trivial question because, sorry, let me restate it. If the system is everywhere contractive, then it's a trivial question, okay? Because the radius of the system will only get smaller. But now imagine that there's regions in the state space where the diameter of the sets gets bigger. Then in order for this to not go to infinity, there needs to be transitions to other states where it gets smaller. So you can temporarily go to the regions of the states where it's not contractive, under the condition that later you go back to some contractive region to go back and stay under this global limit epsilon max. And so we need to select transitions, and this is known in mathematics as a problem, and it's not easy to solve. So we've taken a heuristic approach. We identify a large set of initial transitions. This can be easily done, this initial set, simply by, for example, taking the entire reach set of the abstract states. You see which abstract state can reach which other abstract state. So this is relatively easy, this part. And now we iterate. Basically, we have a superset of what could be a solution to the set of transitions. And then we prune, okay? We take away transitions. And the way we do this is we have this giant this is a giant linear constraint. We see if for the current selection of transition it's satisfiable. If yes, then we have a solution. We've solved our problem. And if not, then there's these properties of linear programs where we can extract information about how far are you away from satisfiability to remove constraints. Okay, so we analyze the linear programming. There's different techniques. There's like irreducible, infeasible subsystems of the constraints that give information. But we used very, very easy but very performant would be just look at negative residuals. So basically, which of the inequalities are that should be satisfied are the left-hand side is the margin between the left-hand side and the right-hand side. Okay, so you need some way to identify the problematic transitions, and then you group them, and then you iterate again on the new set. Okay? So a simple algorithm that leads from a large set of transitions and throws away the transitions that seem problematic. Okay, and the end, if it terminates, then we either have an empty set or a set for which we have an abstraction. And now what we don't claim is that this heuristic gives the largest possible set. As I said just before, the logic finding the largest possible set of transitions is a NP-complete problem. So we don't want to go there. So on to some examples to illustrate this. Let's say the inverted pendulum. Here is the operator F for the inverted pendulum. I think this is on continuous time. We work in discrete type, so this has been replaced by the integration step over some fixed time step to get to discrete time. Here on the right-hand side, you basically see what the vector field is like. So this is inverted pendulum is unstable. You see the trajectories for some constant input, they spiral outwards. Okay. So here, this is certainly not contractive. Okay, this is if I take any set of states here, it gets bigger as time goes on. And so we don't have, there's no discrete bisimulation for this system. Yeah. Now applying to our approach to this inverted pendulum leads, so with these feedback matrices, we can make the system contractive everywhere. So basically, everywhere the closed loop dynamics have eigenvalues strictly smaller than 1. Okay, and it means that we can make this deterministic policy abstraction. So here is an actual plot of one of these abstractions. Again, on the left, here's the vector field, so to give you some intuition of what the vector field would do. And then on the right-hand side, on the same scale, you see the discrete states. Now, we don't show, these are overlapping cells, but they're just symbolized by nodes. And you see the many, many transitions that connect these nodes. Each transition corresponds to applying a feedback policy, okay? And then it goes from one discrete state to the next discrete states. And the image of applying this policy is strictly contained in the new abstract state, okay? So you see lots and lots of transitions, but not all of them lead to states that where in turn you find a next successor state and so on. And so what we did, if you think of this as a solution to the supervision problem, what we're interested in is that there's always a successor, okay, and even more that we can always go back to the initial state or some other state that is useful. And what we more useful is a vague concept, but what we applied here is basically we identified the strongly connected components, because this seems to us an essential property of a system that's operating in a safe manner. Yeah? So say here the strongly connected component is illustrated in gray. Okay. The equilibrium would be here in the center. So if you're in any one of the gray states, you can go to any one of the other gray states. There is always a path from any one of the gray states to the other. Okay. And we have the policy for each transition. You have the policy that realizes this on the concrete system. Maybe some stats on this graph. The number of transitions that you see here is 835. For each discrete states, there is an average out degree. So the number of successors is 6.9, which means that our abstraction actually allows us to choose. Okay. Yeah, as I said, the ones that are in dark gray, that's a strongly connected component. Okay. And we can directly use this abstraction online as a supervisor, because recall that we have these policies. So a policy is always a set of actions. And so we can see for the nominal controller, a simple check is the proposed action part of the set. Then we let it do its thing. Yeah, we apply this action, and if it's not part of the set, then we have to pick one of the actions from the set that we know to be good. Yeah, and this keeps us within the gray region. Yeah. Okay. So this is for the inverted pendulum. So sorry. Now, let me show another example. This is the one-pole oscillator. Again, the vector field is shown for the continuous time version, but we discretize this over time. And here, this is unstable everywhere. There's no discrete bisimulation. So let's see what happens if we do our discretization approach. Now, in this example, there is not a feedback controller that realizes contractiveness everywhere. Yeah? So there is regions where the set will get bigger. Okay, and the question is, can we always guarantee that there's for any of the proposed successors, you eventually get small again? So we see you get these abstraction where you know how big it gets, and you know also that there's a global bound, and you know this global bound. So solving the big linear constraint system for this abstraction gives us matrices K, so one matrix K for each transition. Okay, and you can see here the eigenvalues are between 0.7. So 0.7 is much smaller than 1, so it's quite contractive, but it can be as large as 2. So the size of the abstract cell here would be twice as large in the successor cell than in the original cell. Okay, so going around this system here, your abstraction will vary in diameter. Okay. Now, having to compensate for this divergence that's naturally in the system means that we need to invest a lot of energy to this feedback to achieve contractiveness, and this means that we have less degrees of freedom in modifying the nominal output U. So a different U might lead us to different discrete successors. And so the average out degree here is only 2. So we typically only have on average, we only have 2 successors to choose from. So this seems a natural consequence. I come to the end of the talk. So I've presented basically what's a heuristic to build these abstractions. They're not entirely different from what's already out there in terms of abstractions, but they do have the stated goal that they're deterministic and realizable. Okay, they're immediately usable as supervisors of continuous systems, and because the supervisor is permissive in the sense that it only intervenes when necessary. And the way that we find this abstraction is by solving a giant linear program, and this provides abstractions that are deterministic and robust, even in some tricky cases. Thanks for listening.
Okay, and many thanks for your presentation, Goran. And yeah, as you just mentioned, the presentation is now open for discussions. Is there anyone who wants to start with asking a question? Bastian, you have switched on the camera. Do you have a question?
Yes, but I also need to leave, unfortunately, so I was not sure. But I'll ask. Very nice work. I wonder, have you thought, I guess this is the first step, but have you thought about also dynamic partitions where you don't use the same, I think you call it alpha or epsilon, I don't remember, everywhere?
Yeah, we thought a little bit about this, but for now we try to keep the conditions as simple as possible. Yeah, but yeah, this is an interesting question. Intuitively, there is some for special cases. This is relatively easy. So if it's a linear system, you can scale the alpha linearly. But for nonlinear things, it's a little less
Yeah, I'm
strict.
not saying it's straightforward, but it's
Yeah. No, but it's definitely an interesting path. Yeah, you're right.
yeah. Thanks. I have to leave. Thank you all.
Okay, nice seeing you. Bye.
Okay, any further questions? Yeah, maybe let me continue with one or two questions. I think one question maybe it is even trivial. The application that you have shown at the end, your controller was more or less doing a static state feedback. You
Right.
just have more or less a proportional feedback. Your introductory example was a PI or PID controller.
Yes.
How would you do this? Would you just extend the state vector in order to take into account the dynamics? I assume so.
Yeah, so we assume that we have observation of the state. Yeah. So
Mhm.
you would need to have the system variables and the PID
Yeah,
variables part of your state
yeah,
vector. Yeah,
yeah.
yeah.
That means the state of the PID controller is just appended to the physical states.
Oh, I'm sorry. No. So here the PID controller was applied to the pendulum, to this.
Mhm.
Basically, what it does that for your in some state X and Y, and he proposes an action. And now in the PID controller, that action depends on the history. So it does not
Mhm.
only depend on X and Y, but also on what happened before. But nonetheless, we know here the set of actions that are admissible independently of the history.
Okay, yeah.
Yeah.
Okay, I got it. Yeah.
We have the conditions for completeness. So if they're satisfied, then any admissible PID action uh, would also be covered.
Mhm.
So no, you don't need to include the controller state.
Okay, yeah, fine. And the second question that I had is your piecewise linear over approximation. This reminded me a little bit about modeling of uncertain nonlinear systems with the help of Takagi-Sugeno approaches. And there's some people who are using such techniques in order also to stabilize dynamic systems robustly with the help of linear matrix inequalities. They're more or less defining, let's say, a domain over which you want to get your system robustly asymptotically stable. This is more or less, yeah, let's say, some polytopic uncertainty representation that can be derived from this. And do you know of any works where, for example, something like a pre-stabilization in a robust manner using linear matrix inequalities has been compared with your stabilization technique for the choice of the feedback gain?
No, but again, I'm relatively new to this
Mhm.
abstraction and synthesis field, so I don't want to claim exhaustive knowledge of this. I forgot to mention one thing that's important to me. So there is a formalism that's called approximate bisimulation by Antoine Girard and others, which leads to very similar conditions and in a way more elegantly than what we do. So what we do is mainly fixed on obtaining conditions that, one, relate to reachability, and second is that transform it to a linear program. But conceptually, this is these epsilon approximate bisimulations that would be that's a very good formalism for this type of thing.
Okay, thank you. Now let me have a look again at the list of participants. Is there anyone else who wants to ask a question? If so, please unmute yourself. Okay, this doesn't seem to be the case. Then many thanks, Goran, again for your very inspiring talk.
Okay, thanks for
And
the invitation, Andreas.
yeah, and I just have to advertise for the next presentation. It will be again Friday in 2 weeks, the usual time slot. And our next speaker, who is also present today, is Maël Godard. Again, ENSTA, but a colleague from Brest.
Okay,
Okay,
wonderful.
then see you soon. Have a nice weekend. And yeah, we're looking forward to the next talk in the seminar series.
Okay, see you. Bye bye.
Bye.